Hey guys, today what we're looking at is the trapezoidal rule. So instead of drawing rectangles under our curve, how we can calculate the area under curves is using the trapezoidal rule. A trapezium, like what we saw in last lesson, usually gives a much closer approximation to the area under a curve than a rectangle does. So the trapezoidal rule is a formula that uses a trapezium to find the area under the curve. The general rule for the trapezoidal rule when using subintervals or trapezia is given that we have n subintervals or trapezia, we have the integral of a to b of fx dx is approximately our height or h over 2 of fa plus f of b plus 2 lots of our f of x1 plus ... plus our f of x base n minus 1. This is where a equals x of 0 and b equals x of n, and the values x0, x1, x2, and x of n are found by dividing the interval of a is less than or equal to x is less than or equal to b into n equal subintervals of width h equals b minus a on n. Since we have since we have h equals b minus a over n, we can use the following formula. Now, the following formula is found on your reference sheet. This is the formula that we are going to use when using our trapezoidal rule. So for our trapezoidal rule, what we have is of the integral of a to b of f of x dx is approximately equal to b minus a over 2n of f of a plus f of b plus 2 lots of f of x of 1 plus ... f of x of n minus 1. How we can remember this is that our trapezoidal rule is b minus a over 2n of f of a plus f of b plus 2 lots of everything else, so all the other subintervals or trapezia. It's really important to note that 4 trapezia equals 4 subintervals, which equals 5 function values. Let's take a look at some examples. Our first one here uses the trapezoidal rule to find an approximation for the integral of 1 to 5 of 1 over x dx. Now, we are not told how many subintervals, so because we're not told how many subintervals, we have that our subintervals is equal to 1. So therefore, we have 2 function values, and our 2 function values are going to be the values given to us as either end of our integral. And so what this means is that n equals 1. From this, we have that our a value from our formula is our base of our integral, which is 1. We have our b value is the top of our integral, which is 5. Our f of x is equal to 1 over x, and we know that n is equal to 1. What we can do now is we can substitute all of these values into our formula that we have on our reference sheet. So our formula, and we don't need to write our formula out every time, is the integral of a to b of fx of dx is approximately equal to b minus a over 2n of f of a plus f of b plus 2 lots of our f of x of 1 plus ... plus our f of x of n minus 1. Okay. So what we have here is we want to substitute this in. We want to write out our question. So our integral of 1 to 5 of 1 over x dx is approximately equal to our 5 minus 1 over 2 lots of 1. Now what we have is our f of a. Our f of a is equal to 1 plus our f of b is equal to 5. Now because we have only 2 function values or 1 subinterval, we only have our first and our last. What we can do over to the side is draw up a little table showing what these values of our first and our last are equal to. So our first value here is 1 and our last value here is 5. Now, f of 1 is equal to 1 over 1, which is just 1, and f of 5 is equal to 1 over 5. We then substitute these in, so we get 5 minus 1 is 4, over 2 lots of 1 is 2, of f of 1 we already worked out to be 1, plus f of 5 we worked out to be 1 over 5. This is then just equal to 2, because 4 divided by 2 is 2, lots of 6 over 5, which is equal to 12 over 5 units squared, because we are calculating the area under the curve still. For the next example, we have the integral of 0 to 1 of x cubed dx using two subintervals. So our two subintervals here means that we have three function values. So we always have one more function value than subintervals, and our subinterval is what our n is equal to. We have that our a is equal to 0, our b is equal to 1, our f of x is our function of x cubed, and our n is equal to 2. Now, what we like to do is we like to draw up our table. So we have our x of our fx, and our x values, we need 3 x values. So we know our first x value is our a value of 0, and our last x value is our b value of 1. Now we need to work out what number is directly in between 0 and 1, and that is 0.5. We then work out our f of x. So our f of 0 is just 0 cubed, which is 0. Our f of 0.5 is 0.5 cubed, which is 0.125. And our f of 1 is equal to 1 cubed, which is just 1. We then substitute this all into our formula. So we have our integral of 0 to 1 of x cubed dx is approximately equal to b, which is 1, minus a of 0 over 2 lots of our n of 2, lots of our f of a, which is f of 0, plus our f of b, which is f of 1, plus 2 lots of everything else. So our everything else is just our f of 0.5, So then what we need to do is we need to substitute these values in. So we'll have that 1 minus 0 is just 1, 2 times 2 is 4, then f of 0 is 0, plus f of 1 is 1, plus 2 lots of our f of 0.5, so 0.125. This is then just equal to a quarter, lots of 1.25, which is equal to 0.3125 units squared. Okay, our next example, we're going to use the trapezoidal rule with 4 subintervals to find an approximation for the integral of 2 to 3 of 2 over x minus 1 dx, and we're doing this to 3 decimal places. So we have 4 subintervals. So because we have 4 subintervals, what this means is that we have 5 function values, and we have a total of n equals 4, because n always equals how many subintervals we have. We are given that a equals 2, b equals 3, f of x is equal to 2 over x minus 1, and n, like I said before, is equal to 4. We then want to draw up our table. So with our table, we'll have x, f of x, and we want to have 5 values for this table. So our first value will be 2, our last value will be 3. We then need our values in between, so we're splitting 2 and 3 up. So we will have 2.25, 2.5, and we'll have 2.75. We then need to substitute these x values into our function of 2 over x minus 1. So when we substitute in 2, we get 2. When we substitute in 2.25, we get 1.6. When we substitute in 2.5, we get 1.3 repeater. Now you want to make sure that you store this number in your calculator because this is the number that you're going to substitute in later, the whole calculator value. Now we have substitute in 2.75, we get 1.14, and when we substitute in 3, we get 1. We then want to put this all into our formula, so we have the integral of 2 to 3 of 2 over x minus 1 dx is approximately our b of 3 minus our a of 2 over 2 lots of our n of 4 of our f of our first, which is 2, plus f of our last, which is 3, plus 2 lots of f of everything else, so 2.25, plus f of 2.5, plus f of 2.75. Got to work out how many brackets there. So then this approximately equals 1 over 8. Our f of 2 is 2, plus our f of 3 is 1, plus 2 lots of everything else is 1.6, plus 1.3 repeater, plus 1.14. And like I said before, we need to make sure we're putting our whole calculator values in, not rounding early. When we do this, we get 1 over 8 of 11.15238,095. And then an eighth of this is 1.3940619, which we've been asked to correct to 3 decimal places, so it's equal to 1.394 units squared. Okay, our next example, we want to use the trapezoidal rule with 7 trapezia to find an approximation for the integral of 0 to 14 of t squared plus 4dt. So we have 7 trapezia. Now trapezia are exactly the same as subintervals, so that means we have 7 subintervals, which means we have 1 more function value, so we have 8 function values. And so our n will equal our 7. Our a value we're given is 0, our b value we're given is 14, our function f of t in this case is t squared plus 4, and our n is equal to 7. We are going to do up our table, so we have fx, we'll have 0, and we're going between 0 and 14 and splitting it into 8 values. So we're going to have 0, 2, 4, 6, 8, 10, 12, oh, so close, 14. And there we go. So then when we substitute in our x values into our function, t squared plus 4, we get 0 squared plus 4 is 4, 2 squared plus 4 is 8, 4 squared plus 4 is 20, 6 squared plus 4 is 40, 8 squared plus 4 is 68, 10 squared plus 4 is 104, 12 squared plus 4 is 148, and 14 squared plus 4 is 200. We then are going to use our formula for our integral of 0 to 14 of t squared plus 4 dt is approximately our b of 14 minus our a of 0 of 2 lots of our n of 7, lots of f of our first, which is f of 0, plus f of our last, which is f of 14, plus 2 lots of everything else. So f of 2 plus f of 4 plus f of 6 plus f of 8 plus f of 10 plus f of 12. Yep, just fit it in, all the brackets as well. So this is equal to 14 over 14 of f of 0 is 4 plus f of 14 is 200 plus 2 lots of f of 2 is 8 plus f of 4 is 20 plus f of 6 is 40 plus f of 8 is 68 plus f of 10 is 104 plus f of 12 is 148. We then have that 14 divided by 14 is 1. All of this added together is 980. So our answer is just 980 units squared. Our last example here is a real life example, and we have a diagram that helps us. So we have a surveyor needs to find the area of the irregular piece of land shown. Use the trapezoidal rule to find its approximate area. Now we need to work out how many trapezia we have here, and therefore how many function values we will have, as our function values is one more than our trapezia. So we have a total of 1, 2, 3, 4 trapezius. So we have 4 trapezius, which means we have 5 function values. So our n is equal to 4 here. We want to draw up our table straight away. So we'll have f of fx. And what we have is down the side here, we have our x values. And going up, we have our f of x values. So when x equals 0, that's our first one here, our f of x is 3.7. Then when f equals 1, our f of x is 5.9. When x equals 2, our f of x is 6.4. X equals 3, we have 5.1. And when x equals 4, we have 4.9. This means that our a is equal to 0, because that's our first x value. Our b is equal to 4. Our n is equal to 4 as well. Because we're not actually being given an integral, we are calculating the area of this irregular piece of land. So we write area equals our b minus a, or is approximately our b minus a over 2n, lots of f of a plus f of b plus 2 lots of everything else. Okay, so then we can substitute this all in. So our b is 4 minus our a of 0 over 2 lots of our n of 4. Our f of a is our f of 0 plus our f of b is our f of 4, plus we then have 2 lots of our f of 1 plus our f of 2 plus our f of 3. All the brackets to end it. So this is 4 over 8. Lots of f of 0 is 3.7 plus f of, that's meant to be f of 4 is equal to 4.9 plus 2 lots of f of 1 is 5.9 plus f of 2 is 6.4 plus f of 3 is 5.1, which is equal to, or approximately, because we're just approximating the area, a half. Lots of, oh my gosh, this pen, 43.4, which is approximately 21.7 meters squared, because our dimensions were in meters. So therefore, the area of the land is approximately 21.7 meters squared. What we have now is you guys are going on and doing exercise 702, questions 1 to 6 all.